Swayam Prabha. Digital India. Educated India.
So hi everyone for this second half. So this code generation with LLVM. So we look at how the LLVM code generation happens and what are the basic concepts or basic data structure that is used in LLVM backend. And these are like target specific passes. So different targets, it's different. So to an extent, you can relate it to a API that is provided by LLVM, and in that API for each different target, you have to write the target specific code. Something similar to what you have in an operating system where you have a device driver API where for each different device, the code will be different. So here in the middle end passes, it simplifies the intermediate code. So it uses heuristics, and the typically simplifying means reducing the number of IRs or simplifying the control flow. Then target specific, like you have instruction set that is different for different targets. Registers, number of registers, that is also different for different targets. Then so modification of LLVM IR to target machine need to look at target architecture. So the target and its architecture, its instruction set, its registers, latency associated with instruction set, all things comes into picture. So a detailed study of the architecture is required, and detailed understanding of the architecture is required for code generation to be done. But LLVM provides a generic API through which it becomes a prototype in which you have to implement the target specific passes. So here is a simple LLVM IR instruction where you have a instruction is UI2FP. So unsigned into floating point. That's what UI2FP means. You have a vector of two short integers of number of elements in the vector is 8. You have to convert it to a floating point half. The %1 is a virtual register in the LLVM. So UI2FP is an LLVM IR instruction to convert vector of integer values to vector of floating point values. So how this instruction should be converted to a given machine depends on the machine's architecture, its instruction set. So if you look at ARM machine, the corresponding instruction is UCVTF. You have to map it to that corresponding instruction. Here, so code for different targets will be different. Different targets will be different. So if you look at AR64, that is one of the targets in the LLVM with full floating point 16 pipeline, only one instruction is required. So CVTF, V0 to 8H, V0 to 8H. It's like unsigned fixed point convert to floating point. V is the vector register. The V is vector registers available in the this ARM machine. But if it's not with or without, it's not without floating point 16 or full floating point 16, the number of instructions required is on the higher side. Like the instruction sequence, even like all the vectors which start with all the registers start with these stand for vector registers. Here you're doing it in with a different sequence of instructions. So based on the architecture, even within the same, like if there is no full floating point 16 support, then the number of instructions will be different. So that is target specific. So LLVM provides a target transform info class and passes. So this can be found in lib analysis target transform info.cpp, that LLVM source folder. So this provides access to the code interface. So there will be different instantiation of this passes like AR64, x86, ARM targets. These are all different targets. different targets, there will be different implementations. So process like pass, which can query for details of exact or approximate information about target using details provided in the above class. Like for example, how many instructions are required to convert LLVM IR instruction UI to FP. This could be a query. So there'll be an API which gives such a API function through which you can get that answer. If it supports, if it's a AR64 machine with a full floating point 16 support, the value will be like only 1. If there is no full floating points, full FP16 support, could be some other number greater than 1, so it could be like 8. How big is the cache line? So then get address computation cost gives approximate cost of computation, where get arithmetic instruction cost gives cost of the instruction. Higher the cost, lower the throughput. So when you prefer an instruction which does a conversion which has lower cost. So pass and target transform info is like target transform info class here. A pass can query like how many instructions for this, how many target or machine instruction for this LLVM IR instruction. So this can be a query to the class, the target transfer info class for a given target. Then it could be answer could be like 8. What is the cache line size? The answer could be like 8. Could be like 64. So here, this passes that you have done in LLVM IR could be has some similarity in the LLVM code gen passes, which is done on machine IR. And target instruction info is an interface to description of machine instruction set. So LLVM has a class machine instruction. So some function present in target instruction info class is listed below, like get return of code, get instruction size in bytes. It takes an argument like a machine instruction. This is a machine instruction class provided in the LLVM. Then get load store with rich width. So so many functions or API functions available in the target instruction info, which need to be filled with the code for that specific target. This is a code which I just copied from my machine's code, like lib analysis, AR6 instruction info, CPP file. This function is can get instruction size in bytes. The argument is machine instruction. Then inside that, the code is written to implement it. So it unnecessarily asks this machine basic block, say machine function, which I briefly mentioned in the first part of the lecture, where you had a code to have to iterate over all the instructions in the function, and also code to iterate over all the functions in the machine function. So function correspond to LLVM IR, machine function correspond to the LLVM MIR, machine intermediate code. So these functions are there, like in that these are like all hardware dependent code, like that AR64 or inline ASM, or this all hardware dependent code. This is where you fill out APIs and related to like how you do look at the device level code in an operating system or a device, where you have these functions like open, read, write, close, send, receive. Only here there are so many API functions, and it's a responsibility to fill this with that code. So machine dependent optimization, like here, there is str x1, x1, x2, sp minus #8, sp minus #8. So here we are storing 2 integer value to the stack. So this can be replaced by stp, x1, x2, sp minus #16. This is a single instruction. Where str instruction, like str in small case, instruction store a register value into memory. STP, also in small case, HTTP stores a pair of registers value into memory, that is AR64. So whether such transformation is possible, that is dependent on the machine. Like in one machine it's possible, one machine it may not be possible. But look at the entire architecture, instruction set, everything for conversion of LLVM IR into a machine code for machine dependent optimizations and transformations. So this optimization does not work on LLVM IR because STR and STP, they are like machine instructions, and it does not work on LLVM IR. So this is done by after instruction selection. So like STR is an instruction available in ARM machine, and if you have a R64 which support STP optimization, this happens. So this is about point to be noted in machine dependent code optimization or machine code generation. So coordination process and machine IR, like coordination pass done after instruction selection. So
sorry to interrupt. I have a question in the previous slide.
Yeah.
Would this transformation work even if we have some instructions in between these two stores?
As far as like, as you know, like you can have instruction reordering, right? It is valid. Like if there are 2, 3 instructions, 4 sequence of instructions which are mutually independent, they can be executed in any order, right?
Yes.
So that may require some optimization where you need some analysis, like use step chains, and then you transform the instruction sequences. And unless it's semantically correct, but to reorder the instructions and do, like if say STR is comes as ith instruction, first STR as ith instruction, second k instruction where I greater than k. It is possible to have it at I as far as x2 is not modified, or in between the stack locations are modified. Thus, standard fundamentals, like as far as semantically equivalent transformations are possible, it's okay, maybe.
Okay, and yeah, I mean, that's, yeah, thank you.
So yes, at the end of the day, like whatever optimization you do, semantically preserving transformations, like
Yeah, would you say this is an example of operator fusion?
Operator fusion.
I mean, it's a store instruction, so it's not exactly an operator, but this looks very similar to what you would do in operator fusion.
Yeah, something like 2 instruction being converted to 1, like you say about exactly instead of doing 2, you're doing 1, but the instruction is different. So yeah, it's not like that. I'm not sure like you take it. So yeah. So the important point here is that it's architecture independent, so it does not work on LLVM. So
All right, thank you.
So this coordinate passes and machine IR done after instruction selection. So coordinate pass does not work on IR, like coordinate passes work on machine intermediate representation. There is similarity between MIR and the IR. IR is like the middle end pass intermediate representation, that is target independent, or you can do a lot of transformation in a target independent way, so that it's generic, like might have seen some data flow analysis techniques. Even SSA form is a good thing in FPR, and then some common sub-explain elimination. There are so many optimizations that you have done. It's possible in a target independent way, but once you have in machine IR, it depends on the target. So MIR, as an example, percentage to GR64 instruction, and these are like, so you have a IR, then After instruction selection, you have get a MIR. So the instructions are like target dependent instruction. Then you have assembly printer that do the prints the assembly. But in between have some, in the MIR result, we can have some passes to optimize, like given in the previous slide. This is the high level picture, but there will be so many intermediate passes. So x86 MIR, like for is not equal to AR60 for MIR. Like all are mutually independent. So due to this, after instruction selection, these instructions will be different. So the MIR is like I mentioned here, like virtual registers like %2, %0, %1. Because we have not done with the register allocation, just done with the instruction selection, like add 64 here, or that's the instruction for the AR64 machine for addition. Physical register is E flags. The target specific code, operand. So there would be like liveness indicator flag, like kill means flag means last use of register. That means flag means unused definition. So this is the meaning of these flags in this MIR. And this, even the result of register like percentage, that is also called as operand. So IR versus MIR, we can have a comparison. So we have already done with the LLVM IR passes. So middle learn passes on IR does not change IR representation, like this need not necessarily change. Like that could be a better word. Percentage results are percentage R and percentage R2. Code didn't pass on MIR changes the MIR representation, like just the image representation. Maybe MIR after live analysis might become like metadata being added. Like it's possible to add metadata even in LLVM IR. Generally, we don't do unless very essential. So then it's added a metadata. After register location, instruction might become as given below. Like it's after register location, it's not in SSA form because the virtual registers are being replaced by the physical register. So each register will be loaded and stored many times. So single assignment to a register is not valid. So code.
I have one question here. So for IR, we consider that we have infinite number of virtual registers, and so is it same for MIR or not?
MIR after instruction selection, it's okay. After register location, it's not.
Okay. Thanks.
So the thing is, it goes on different passes. Like this is a, I would like to say this is a high level picture, but it's not like MIR directly being converted to an assembly. There will be some intermediate passes, and that final step is assembly printing. So one of the paths will be like register location.
Okay. Thanks.
Even adding metadata is possible even with IR also, not just with MIR. So you have this instruction selection, then liveness analysis, and register location. So here I put a bar here because this left half is like SSA4. This is not in SSA4. Input is like a LLVM middle-end IR or LLVM IR. After instruction selection, you do some liveness analysis, then do register location. These are some important passes, but not limited to this. So,
sir, I have a question in the last slide.
Yeah.
So if we do this SSA form conversion and then do the register location, then it will automatically increase the register pressure, right? Because it will have more and more variables in the code. So how we deal with
this SSA form conversion, this 5 elimination is there. it's covered in the lectures, in the previous lectures. Phi elimination, it creates copy statement at the end of the basic block and the beginning of the phi instruction. Phi is replaced by copy statements. So it need not improve the register pressure. That's all I want to say, because after we are doing a register allocation with which uses something I covered in the first half, like when it is loop or even its function. This coordination, that loop was taken because it has a few number of basic blocks, like 4 basic blocks was the example, and as a package, when you make it for a function, we are not doing a local register allocation, that is applicable for one basic block. We are doing a global register allocation that is for the entire function. Such a scenario, it need not affect.
Okay.
So phi elimination is done by adding copy statements. Is it covered?
Yeah, and some briefly it is being touched upon.
Yeah. So if you look at the middle and then code gen, like IR and MIR passes, like there is function in this what is shown in the red that we are going to see, like machine function is there, basic block, there is machine basic block, instruction, there is machine INSTR, like machine instruction is there with this class. Middle and like dump all instruction in a basic block, you can like something like this can be done, where BB is a basic block, then you do this extreme an instruction, then extra dump, or then dump all instruction in a machine basic block, can do something like this also. Sorry, there's a typo, there's a space here, it should not be there, it's a variable MBB. MBB is variable, space is a typo, then MI dot dump. So some similarities there, like at the with respect to writing a backend process similar to a middle end pass. But for each target, the code will be different, instruction will be different, that you have to inform that is incorporated in the target transform info class and target specific classes. The passes, you can use those APIs available with that target specific classes and get details and do the passes. Difference in IR and MIR, like check instruction is conditional instruction, like it's a middle end pass, like check instruction is conditional instruction in code gen pass. This is one instruction where you have branch instruction being casted, using a dynamic cast, and which we hold dynamic casting cannot hold it code gen pass. So there will be some differences where what exactly found in the IR may not work in the MIR. So we'll go through this, like people optimization, like optimizing branches. So suppose you come across a code like this, like CS increment W9, W0, W0 condition, DB and set W9 #0 #0x44. As I'm repeating, like this is the MIR, so instructions are machine specific. So CS sync, like RAM processor, like result R1, R2 condition. So condition select increment. If condition is true, result is first argument, else the result is like W9 in this example. The first argument is the result register or destination register. So in condition true, the result is the first argument. So W9 will be assigned W0. Else is like second argument +1. So it will be WZR +1. WZR is a register available in the CAM processor, that's 0 register. And TB and set is W9 #0, checks whether the 0th bit of W9 is not 0. Then you branch to 0x44. So here, if a 0th bit of W9 is not equal to 0, branch to 0x44. So if you look at the CS increment, both the registers are W0 register. The register will have value 0. So if the condition is true, W9 will become 1. The condition is, if condition is true, it will be first argument, that is 0 register. Condition is false, then it will be 1. If because 0 register has a value 0, condition is false means second argument plus 1. So W9 will become 1. So when W9 will become 1 is when the condition is false. So condition is, so typically this implies if condition is false, branch to the address 0x44. So like a machine dependent instructions and the machine dependent code transformation. So this can be converted to a branch on condition where you take the negative of this condition, and if that the condition is true, you can branch to this address 0x44. Because if condition is false, then W9 become 0 register, that's the last argument, plus 1. So then that will become make W9 1 and W9 become non-zero. For that to happen, negative of the condition should be there. It can be made like if negative of the condition is true, then branch to 0x44. You can look for a harder instruction available in our AR64 so that it can be converted to one instruction. So CSing, if condition is true, W9 is 0, else W9 is 1. WZR is 0 register. So like if condition is false, branch to 0x44. Single instruction possible. So it's like so let's say BCC instruction like available, using which can transform this code into a different machine code. I'm not going in detail about the architecture. So such small optimizations are possible.